Hi there once again, and welcome back to this video lecture in ABE153. And this video will be doing our second sample problem for the topic on fatigue loadings. This problem is taken from the textbook by Mott et al. This is Machine Elements in Mechanical Design, and this is example problem 5-2. Now the problem says estimate the actual endurance strength of a SI 1050 cold drawn steel when used in a circular shaft subjected to rotating bending only. The shaft will be machined to a diameter of approximately 1.75 inches. Right, so this ASI 1050, the properties of this can be obtained from the tables from the textbook. Right, so let's write our solution. Okay, so first, the given data are, so we have AISI 1050 cold drawn steel, and it says here it is machined and rotating bending. The loading is rotating bending, and this is circular shaft, and also the diameter is equal to 1.75 inch, or we'll also include the equivalent millimeter, 44.45 millimeter. And based or from the table, this is the SUT. The SUT, the ultimate tensile strength, is equal to 690 megapascals. Right? So this is from the table. Okay, so the next step is to solve for the endurance limit. Okay, so SE is just simply equal to 0.5 SUT. Why? Because this is less than 1,400 megapascals. So this is our working equation. 0.5 times 690 megapascals. And this is equal to 345 megapascals. Right, so we have the endurance limit based on the standard specimen, and the next step is to solve for the factors. Right, so for the factors, let's start with CF, the surface finish factor, and the CF is equal to A times the ultimate tensile strength raised to B. And the value of A, since this is machined, if you go to the table, this is 4. Right, so this is machined, and it says here 4.51, and the exponent is negative 0.265. Right, so 4.51 times the ultimate tensile strength, 690 raised to negative 0.265, and this is 0.798. Right, so that's the surface finish factor. Then the next one is the size factor. Okay, so for the size factor, CM, oh sorry, this is CS. So CS, since our size is 44.45, then the working equation would be D, the diameter, divided by 7.62 raised to negative 0.11. And if you substitute all the values, the value of this 144.45, then this will be 0.824. Okay, what else? The material factor, this is just, the material factor is since this is steel, then this is it's just 1.0. And for the loading load type, factor CL is just 1.0. Why? Because this is just rotating bending only. So the value of CL is just 1.0. And for the temperature factor C sub T, this is just equal to 1.0. Why? It's just simply because the there is no specifications here that it is subjected to some elevated temperatures or temperatures higher than I think 450 degrees C. Right, and for the stress concentration factor, as I've said, since we don't want to go to the, I mean, we don't have the means for the data and things like that. Or if we, I mean, if we have, then I think it's just it requires time. Then I guess we just have to skip the stress concentration factor, and therefore, the corrected endurance limit is, right, so SE prime is equal to the factors. So we have the surface finish times the size factor times what else? Times the theoretical endurance limit. So CF is 0.798 and this one is 0.824 times this endurance limit, this 345 megapascals, and this is 226.85 megapascals. Right, so if you compare this, this one is or this one has a lower value as compared to this endurance limit value. All right, so this is just I think pretty straightforward, because once you have the data, once you have the ultimate tensile strength and the data right here, then you can just simply select from tables or select appropriate equations for the factors. So once you have all the factors, then you just simply multiply that to the endurance limit in order to obtain the corrected endurance limit. Alright, so let's do our last sample problem. This is 6.3. And this sample problem is taken from the textbook by Shigley, and this is example 6-8. And the problem says a 1015 HR, this is hot rolled steel, has been machined to a diameter of 1 inches. It is to be placed in a reversed axial loading for 70,000 cycles to failure in an operating environment of 550 Fahrenheit. Using ASTM minimum properties, estimate the endurance limit and fatigue strength at 70,000 cycles. Right, so that's actually the problem, and I just included right here that for this temperature range, the ultimate tensile strength is 49 ksi or 337.84 megapascal for the specified temperature. Now, just a couple of notes here is that once the material is subjected to higher temperature, there's actually a decrease in the strength. So instead of, let's say, we have a yield strength of 250 megapascal for static loading tensile, I mean, if we have a 250 megapascals, then if it is subjected to higher temperature, then that's not going to be 250 pascals anymore. Right, so that's just the just a side note. Right, so I have given this already. I just included the data right here so that we don't need to solve that. So the SUT is equal to 49 ksi. Right, so let's solve now. Now for the solution, let's obtain the given data. And the given data is we have a 1015 hot rolled steel bar, and the surface finish is machined, and the diameter says here the diameter is 1 inches. So diameter is equal to 1 inches, which is equal to 25.4 millimeter, and the loading is actual loading, reversed actual loading, and we have 70,000 cycles. Right, so here's our data and also the SUT. This is 49 KSI, or 337.84 megapascals. Okay, so once we have the given data, then let's solve for the endurance limit. Right, so SE prime. So SE prime is equal to 0.5 times the, and right here this is, I think we'll just use the megapascals, so 337.84 megapascals, and what we get here is a value of 168.92 megapascals. Right, so here's our theoretical endurance limit. So the next one is to solve for the factors, or the marine factors. Right, so CF. So let's first start with the surface finish. So for surface finish, recall that our working equation is the ultimate tensile strength times A, and this one is raised to B, and if it is machined, the value of A is 4.51. so just I think the same with our previous sample problem. This was negative 0.265. So if we substitute the value, this is 4.51 times SUT, right? So we have we'll use this megapascals, 337.84. By the way, this value right here, this 4.51 and negative 0.265, these are based on megapascals, I think, right? So that's why it's very important very important to know if our units is in megapascals or in English units. Right, so for the B, this is negative 0.265, and this is 0.959, right? Okay, so the next factor is the size factor, so CS. For the CS, since our diameter is our size factor is diameter is 25.4, so the working equation would be this one, 7.6 d all over 7.62 raised to negative 0.11, and if you substitute the value of d, what we get is 0.876. And for the loading factor, since this is reverse actual loading, then CL is equal to 0.85, and for the temperature factor, this is below 450 Celsius, then this is just 1.0, and therefore the corrected endurance limit is SE is equal to CF times the size factor times the loading factor times the this endurance limit right here. So this is 0.959 times the size factor of 0.876 times the loading factor of 0.85 times the value of SE, which is 168.92. So this is 168.92, and if you do the math, what you get is 120.62 megapascals. Right, so that's the corrected endurance limit. Since we now have the endurance limit, then we can proceed further to our computation regarding the strength at 70,000 cycles. So the next step is let's graph first. If this is our ascent curve, and we have this curve right here, and at this point, recall that this is 10 to the 3, and this point is 10 to the 6, and 70,000 cycle, that's actually 7 times 10 to the 4, so somewhere right here. Okay, so solve first for, or let's write here, determining the fatigue regime. Okay, so we are right here. Okay, so let's solve first for F. Okay, so F is if we check this graph right here, we have here in the horizontal axis, that's the ultimate tensile strength. The minimum right here is 70, and our given value is 49, right? 49 ksi. So that means that the F value would be 0.9. So let's write here F is equal to 0.9, since the ultimate tensile strength is less than 70 ksi. Okay, so the next step then is to solve for A, right? Because in this region, our working equation is just simply A n to the B. So solve for A, and the working equation is A is equal to S times the ultimate tensile strength squared divided by the endurance limit, and this is now the corrected endurance limit. Is 0.9 times our ultimate tensile strength, and we can use these megapascals. This is 337.84 squared divided by our, okay, not this one, because this one is based on the standard specimen, but rather we will use this corrected endurance limit of 120.62 megapascals. And what we get here is 766.4 megapascals. Alright, now that we have the value of A, we can now solve for the value of B. Solve for B. So the B, the working equation, is negative 1/3 log of F times the ultimate tensile strength divided by the endurance limit. Okay, and this one is 0.9 times 337.84 divided by 120.62, and what we get here is negative 0.1338. Okay, so Sn at 70,000 cycles is, this is our working equation, and if we substitute all the values, what we get is an Sn value of 172.26 megapascals, or in terms of KSI, this is equal to 24.98 KSI. Okay, so let's review our procedure. So the given here is a steel that's 1015 HR, and we have these conditions right here, and the main question is that we are to find the strength or estimate the endurance limit and fatigue strength at 70,000 cycles. Okay, so we are considering now the actual conditions, and we have to take into account the deviations from the standard specimen. So the first step that we need is to obtain the given data. We just have to write it down so that we can follow through, and we write also the ultimate tensile strength. Okay, so once we have all the data, then we can estimate the endurance limit, and the endurance limit is just simply 0.5 or half of the ultimate tensile strength, right? So take note that this endurance limit is just simply based on the standard specimen conditions. Okay, so after that, we solve for the marine factors, we solve for the surface finish factors, we solve for the size factor, the loading factor, because this one is in reverse axial loading, so we are to use the 0.85. And once we have all the factors, then we can just simply solve for the corrected endurance limit. And by the way, regarding the factors, there's also another one right here, that's reliability factors, C sub R, and we just didn't solve it here, but you can go through the textbooks if you want to also take that into account. Okay, so after that, once we have this corrected endurance limit, then we can now proceed further to our problem of finding the fatigue strength at 70,000 cycles. So 70,000 cycles, that's 10 to the 4, and we are in this region right here. And the equation, the strength equation, this is Sn is equal to A times N to the B. So we first solve for the F, that's the fraction, fatigue fraction, and we found out that this is 0.9. And after that, we solve for A, and we solve for B. And once you have the A and the B, and since you are also given the value of the number of cycles, then you can solve for the fatigue strength. So the fatigue strength is 172.26 megapascals. I guess that's all for our fatigue loadings, and just take note that we only consider the fully reverse type of fatigue loadings, and there's still another type, like I've mentioned, it's the fluctuating stress, right? So there's, the solution for finding or the analysis of fluctuating stress is different than the ones we did here, and I think that will encompass our topic on failure theories, right? So that's why we'll just stop with this um, fully reversed stress. Okay, so I hope that you learned a lot in this topic, and in the next video, we'll be moving on to our next topic on failure theories. So, see you in the next video.